Welcome to Regal Learning Hub. This is another tutorial. This is the part 2 of the topic indices or powers of natural numbers. If you have not seen the part 1, make sure you scan through our channel to actually locate this video. Additionally, you can check in our video description for the link to this video. Before you continue, don't forget to subscribe to the channel and click on the notification bell so they can always be notified anytime I post videos like this. You're welcome once again. Thank you. Writing numbers as products of their prime factors. The prime factor of a number is a prime number that divides that number without a remainder, if you can recall. For instance, 3 is a prime number, and 12 divided by 3 is equal to 4. So we can say that 3 is a prime factor of 12. Instructive example 3. Write 72 in its product of prime factors. Now, answering the question, we can use the factor tree to compute that. Now we ask ourselves, which prime number can we use to divide 72? Or the least prime number we can use to divide 72? And the answer is simply 2. So now, we ask ourselves again, 2 times what will give us 72? And that's going to be 2 times 36. Now 2 is a prime number, so we put it in a box. But now 36 is also a composite number, which must be expressed further. So we ask ourselves again, what is the least prime number or the smallest prime number we can use to divide 36? And again, it is 2. And again, 2 times 18 will give us 36. Expressing further, you can observe that we can also divide 18 by 2. And again, multiplying 2 by 9 will give us 18. Now focusing on 3, you can realize that we cannot use 2 again, but rather the next prime number we can use is 3. And as you know, 3 times 3 will give us 9. Now, that would mean that 72 can be written as 2 times 2 times 2 times 3 times 3. And this can be expressed as 72 is equal to 2 to the power 3 times 3 squared. And that is its product of prime factors. Alternatively, or using an alternative method, we can also express it straightforward. And again, 72 can be written as 2 times 36, but 36 is not a prime number, so we'll proceed further. And that would mean 72 is equal to 2 times 18, and the 2 times 18 there represents the 36, which we can go further by writing it as 2 times 2 times 2 times 9, where the 2 times 9 represents 18. And now finally, 2 times 2 times 2 times 3 times 3, and where the 3 times 3 would represent 9. So we can say that 72 again can be written as 2 to the power 3 times 3 squared. Using the last alternative method, which I wish to call the prime divisor table, we look for the prime divisors that can divide 72, and the first one we know is 2. And dividing 72 by 2, we come up with the number 36. We ask ourselves again, what is the least prime number that can be used? What is the least prime number that can be used to divide 36? And it is simply 2. And again, 2 divided by 36 will give us 18. And once again, 2 can divide 18. So dividing 18 by 2, we come up with an answer 9. Now we can't use 2 again, but rather we can use 3, which is the next smallest prime number we can use to divide 9. So 3 divided by 9 will give us 3. And now finally, we can divide the 3 there by itself, and that will give us 1. Now we can express the prime divisors as a product that will give us the number 72, which is going to yield the answer. 72 is going to be equal to 2 times 2 times 2 times 3 times 3. And that would again simplify to the answer. 72 is equal to 2 to the power 3 times 3 squared. The laws of indices. Law 1. When multiplying powers of the same base, add the exponents and write the result as a common base with the exponent sum. That is, a to the power m times a to the power n is simply going to be equal to a to the power m plus n. Proof using a squared times a to the power 3. A squared times a to the power 3 is simply the same as a times a for the a squared and a times a for the a to the power 3. Now multiplying and removing the brackets, you simply realize that the answer is going to be a to the power 5. And that is by adding the exponents if you want to use the laws of indices. Now, do you note that the sum of the exponents, that's the 2 plus 3, is 5, which is the same as the sum of the exponents? Thus, a squared times a to the power 3 is simply going to be equal to a to the power 2 plus 3, which is the sum of the exponents, and which will give us the answer a to the power 5. Law 2. When dividing powers of the same base, subtract the preceding power from the preceding power and write the result as an exponent of the common base. That is, a to the power m divided by a to the power n is simply going to be equal to a to the power n, a to the power m minus n. We're going to prove the second law using a to the power 5 divided by a to the power 2. A to the power 5 divided by a to the power 2 is simply equal to a to the power 5 over a squared. Equaling and expanding, you get to realize that a to the power 5 is the same as a times a times a times a times a over the a squared, which is the same as a times a. Now, splitting further and writing them as if they were gotten by multiplying individual expressions, what you realize is that a divided by a times a divided by a will represent the use of all the a's that are the denominator, or the products of a's that are the denominator, leaving out a times a times a. Now as they divide, we end up getting 1 1, and multiplying the rest of the a's left, we are sure of coming up with the answer a to the power 3. Do you observe that the differences of the exponents, that's 5 minus 2, is the same as 3? Thus, we can say that our second law is proven. So, when you are dividing powers of the same base, you subtract the exponents as shown on your screen. Law 3. When a power is raised to a power, write the product of the exponents as an index of the base. And that is to say, a to the power m all to the power m is going to give us an answer a to the power m times n. And now let's prove using a squared to the power 3. Now, a squared to the power 3 simply means that we multiply a squared by itself 3 times. That is a squared times a squared times a squared, as shown by the power 3. Expanding further, our a squares become a times a for all the expressions that have been multiplied. And removing the brackets and multiplying, we come up with the answer a to the power 6. Do you notice that the product of the exponents 2 times 3 equals the answer 6? Again, by the third law, a squared all to the power 3 also gives us a squared times a squared times a squared. And by the third law, what do? We add the powers, or we add the exponents. And that's the same as multiplying 3 by 2. After all, repeated addition is multiplication, and that would give us the answer a to the power 6. Law 4. A non-zero number raised to the power 0 equals 1. That is, if I have a non-zero number, say a, raised to the power 0, this expression represents 1. Let's prove this. We know that a non-zero number divided by itself results to 1. Thus, if I have a raised to the power m divided by a raised to the power m, I should get the answer 1. So by the second law, a raised to the power m divided by a raised to the power m should be equal to a raised to the power m minus m. Now, connecting the expression to the above expression, we know that a raised to the power m minus m should be equal to 1. But we know that m minus m is simply equal to 0. Now that simplifies our expression to a raised to the power 0 is simply equal to 1. And that proves our formula. Law 5. A non-zero number raised to a negative power is a reciprocal of the positive power of the same base. That is to say, a to the power negative m is simply going to be equal to 1 over a to the power m, which is the reciprocal of a to the power m. We are going to prove using a squared divided by a to the power 5. We know that when you divide a smaller number by a bigger number, you obtain a fraction. And now, a squared divided by a to the power 5 can also be written as a squared over a to the power 5. And expanding both the numerator and the denominator, we have the numerator becomes a times a, and the denominator becomes a times a times a times a times a. That's a to the power 5, as shown above. And now, we can cancel out some of the variables multiplying at the numerator and the denominator as shown on your screen. So you realize that the letters or the variables color-coded red can be cancelled out, and they become 1, leaving 1 over a to the power 3 as shown on your screen. On the other hand, we can use the second law. And by using the second law, a squared divided by a to the power 5 is simply going to be equal to a to the power 2 minus 5. And what do we get? A to the power negative 5. Thus, a to the power negative 3 is simply the same as 1 over a to the power 3. And this proves our fifth. Law 6. When a number is raised to a fraction, the numerator raises the number to a natural power, while the denominator takes a certain root of that power according to its value. And that is to say, a to the power m over n is simply going to be equal to the nth root of a all raised to the power m, or a to the power m over n is simply equal to the nth root of a to the power m. Both expressions are similar and the same. Proof using 64 to the power a and finding its square root. 64 can be written as 2 to the power 6, and that is the same as 2 times 2 times 2 times 2 times 2 times 2. And that will imply that 64 to the power a is simply going to be equal to 2 to the power 6 all to the power a, where our 2 to the power 6, of course, numerically represents 64. Raising both sides to the power half, it will imply that 64 to the power a all raised to the power half is simply going to be equal to 2 to the power 6 all raised to the power a all raised to the power half. Using the third law, we multiply the exponents at both sides. That's going to imply that 64 to the power half a is simply going to be equal to 2 to the power 6 times a times half. But we know that 6 times a times half can be simplified to the answer 3a. And of course, half a is the same as a over 2. And that is going to imply that 64 to the power a over 2 is going to be equal to 2 to the power 3a. And now, as we know, using the third law again, by this time in a reverse manner, we can say that 64 to the power a over 2 is going to be equal to 2 to the power 3 all to the power a. Don't forget, still applying the third law, we can multiply 3 by a to still bring our power back to 2 to the power 3a at the right hand side. Now, that is going to imply that 64 to the power a over 2 is going to be equal to 8 to the power a. But 8 is the square root of 64. Now, what does that mean? We can simply write it as 64 to the power a over 2 is going to be equal to the square root of 64 all to the power a. And that is going to be equal to the square root of 64 all to the power a. That is, we can remove that subscript 2, since when writing square roots, we don't normally include that number 2. Color written as what? Red. Thus, we can say that a to the power m over n is simply going to be equal to the nth root of a all to the power m, or a to the power m over n is going to be equal to the nth root of a to the power m.